Okay, welcome everyone to our December 3rd, 2024 computer vision session for Cohere for AI. My name's Amit Taylor. I'm one of the co-leads for the Cohere for AI community, and I'm also joined by my co-lead, or our co-lead, Benedict. If you want to introduce yourself, Benedict.
Hello everyone, my name is Benedict. I am the co-lead for the Cohere for AI computer vision group, along with Amit, where we try to bring in new speakers as frequently as possible at this time, as frequently as possible, this time Tuesdays, for them to share their research and then for them to elucidate us on the latest SOTA, state-of-the-art innovations in the field. So without further ado, I will return the reins of the program to Amit so he can conduct things with his normal gusto.
Okay. Yeah. So for those of you who are new on today's call, I just wanted to give a quick overview of Cohere for AI. Cohere for AI is a hybrid research lab and open research community dedicated to contributing fundamental research in machine learning. And it works to solve some of the field's most challenging problems while creating more points of entry into machine learning research. And it does this in a number of ways, but I wanted to highlight three of the ways that it does it very quickly before we started with our session this morning. One of the key ways it does it is with a relatively new program that we have at Cohere for AI, which are called Research Office Hours. Research Office Hours are an opportunity for you to connect with Cohere for AI research staff, get answers to your questions about machine learning research and LLMs. During research office hours, you can, dial in and learn more about working with Cohere for AI's open models and data sets. And you can, more importantly, with, folks who are in the industry or who are in machine learning research, share research ideas and get feedback. Sometimes that's difficult to get outside of your PI. So it's great to have, the research office hours where you can go and get some of this feedback. So our next session for research office hours is tomorrow, December 4th. And Alejandro Salamanca runs the research office hours, but tomorrow he'll have a special guest, Julia Krutzker. And Julia focuses on multilingual translation, and she's a mom with kids, so she can also talk about how she does the research with having a family. So that'll be our session tomorrow, and I put a note in the chat as well for how you can join the research office hours. So that's one way that we contribute in terms of the community as far as research is concerned. The other key way is on a bi-monthly basis, I believe, we have the Roads to Research sessions at Cohere for AI. And the Road to Research sessions essentially is a program launched by Cohere for AI that aims to showcase what it takes to be a machine learning researcher. So it highlights aspects that might not be commonly discussed in academia, such as how to generate research ideas, navigating career paths between academia and industry. And more importantly, it gives you a key ideal of some of the soft skills that are needed for research success. So our session tomorrow, and the Roads to Research will have a session tomorrow as well. And the panel conversation tomorrow will be talking about scientific communication. So we'll be joined tomorrow by Jay Alamnar, who I'm pretty sure many of you on the call are familiar with. Also, we'll be joined by Shane Longpre, who's a PhD candidate at MIT. And then Marzai Fadai, who is from Cohere for AI, will also be on the session tomorrow. So again, this is a great way as well for those of you who are interested in the machine learning research to get some more information, especially when it comes to scientific communication, which will be the focus of tomorrow's session. And finally, what we're all here for today, the other way that we contribute to research as far as Cohere for AI is concerned is with our guest speaker sessions. So today, we're excited to be joined by Peng Shaya. Peng is a research intern at University of North Carolina at Chapel Hill. And Peng today will be presenting on RULE, Reliable Multimodal RAG, for factuality and medical vision language models. So with that being the case, with no further ado, I'm going to go ahead and stop sharing and hand off to Peng.
Thank you. Yeah, great. Thanks for the Med and Benic invitation. I'm very happy to be here to give a talk about our recent work on the vision language models. Yeah, I will share my screen.
Okay.
Okay. Could you see my screen?
Yes, we can see it.
Okay. So, hello everyone. Thank you for attending this session. My name is Peng, and I'm now working with Professor Huaxiu Yao at UNC-Chapel Hill. Yeah, today I will present our recent work titled Reliable Multimodal RAG for Factuality in Medical Vision Language Models. So this presentation will dive into evaluating and enhancing the factuality of medical vision language models, a critical need in healthcare application. Yeah, so our research is structured around three key areas. So first is comprehensive evaluation of medical large vision language models. We call it medical LVMs. And the application of retrieval augmented generation, RAG, to improve the medical vision language models. And the future directions involving like post-training of medical vision language models. So I will refer prior work like CARES, RULE, and the Med-LVLMs, and along with our latest developed Med-LVLM to explain how we address the challenge in this domain. So firstly, we need to talk about the medical large vision language models. So what is that? Actually, the medical vision language models are developed by fine-tuning general purpose large language models using medical multimodal datasets. So this fine-tuning process enables the models to acquire domain-specific medical knowledge. It is more like supervised fine-tuning. Yeah, it makes the model to understand all the medical entities and knowledge in the datasets. Yeah, by using this paired data from the medical images and text descriptions, medical vision language models are tailored to perform critical tasks such as medical VQA and report generation. So we started by asking the question, how do medical vision language models perform? So firstly, in our primary work, which is published in Europe's 2024, our evaluation is focused on trustworthiness across 5 dimensions: is trustfulness, fairness, safety, privacy, and robustness. And in this today, I will focus more on the factuality hallucination, which is factuality actually. We use some like VQA format or report generation. We can see the model's response if there is something a hallucination or something incorrect response in that. So we can judge the model if there is any trustfulness issue in the model. So we developed a CARES dataset based on the medical vision language model and a vision language and the image classification dataset. So it is very big and covering a lot of medical image modalities like X-ray, we are familiar, and some pathology and ophthalmology and so on. So firstly, we can see the trustfulness key findings. Actually, the models frequently exhibit factuality hallucination, especially with open-ended question, which is much harder than closed-ended questions. And you can see in our left figure, most of the models have over 50% accuracy errors on our benchmarks. So their performance is very poor, and they have a lot of issue like the uncertainty issue. They are very overconfidence and poor grasp of medical knowledge limits. And then we dive into several dimensions, like a very key aspects in healthcare application is fairness. yeah, we need to evaluate many models in some like age, gender, and racial. Yeah, we dive into these dimensions and we found that actually the best performance in the 40 to 60 group with a drop in accuracy for the elderly due to the uneven data. Yeah, it doesn't make sense. More like a long tail problem. And secondly is for the gender. The gender actually is more subtle, and yet notable in specific data sets like CT and depth. Yeah, maybe it is more like a model train on some few modalities data set. But actually the model performance is actually better. Yeah, and for the racial analysis, it shows that better outcomes for the most of the populations is much better. Yeah, so it do not have seen very balanced results across ages. And secondly, is about the safety. We can find seeing our figures and tables under jailbreaking attacks. Maybe we let the model to say some unsafety response, but the model most of the model will generate the response as usual. But except the lava mat, it will reject our prompt. Yeah. So the accuracy drops for older models. Older models slightly increase in the toxicity under the tox problem, but LavaMed will uniquely show strong performance. Yeah, and however, it's overly confident turning leads LavaMed to be the two cultures, often refusing even for the regular medical questions. So that is we don't want to see. And for the privacy, privacy is another hard problem in healthcare applications. So unlike general models, medical vision language models often lack defenses against queries seeking privacy information. So it failed to refuse such context. But you can see from our table, most of the models may generate response with some private information because they do not train about that. They do not use like the RAHF or some alignment methods to tell the model. You can generate some response containing the privacy information. Yeah, this is quite a problem. And lastly is about the robustness. It is more like a generation problem in the machine learning. So we can see the results in the table 5 and table 6. Medical vision language models struggle with accuracy when the significant noise affects the input images. So even with some like unfamiliar modalities like the red foundation model, it do not train on some like ophthalmology dataset. So it can generate a response when you input some unfamiliar modalities, but it's not what we want to see. Its accuracy is very low, and it will not reject your problem. So we need to make the model much robust, and it can judge the problem even in his knowledge scale. So above is our evaluation work about the medical vision language models. And today we will focus more about the factuality of medical vision language models. So actually, to improve the factuality performance of medical vision language models, there are two key aspects, which is fine-tuning techniques and retrieval augmented generation. So fine-tuning involves adapting general proposed language models using medical multimodal dataset. By incorporating domain-specific data, this model can better understand and generate medical knowledge. But it's very costly and you need a lot of GPU and high quality data. So some recent work have introduced the retrieval augmented generation RAG to enhance the factuality by integrating the external knowledge to the model's output generation process. So it's more like you retrieve most similar report based on your data source, and then just put the similar report to your input prompt, so that the model can get your like in more like in context learning. Yeah, it can get some generate more factual response. So in the firstly, we just use retrieval augmented generation, which is a very promising approach to enhance the faculty of medical vision language models. So we just use like a clip model or some more powerful constructive models. It's more like you input a medical image and it will retrieve some more similar reports based on your database. It will calculate the similarity score based on your input image and all the text reports in your data source, so that it will generate some retrieve a lot of reports in your question prompt. Then the model will generate the more factuality response with aid of this. And we can get some preliminary results. We can see from our figures, and you can see almost all the accuracy has improved, but you can see the precision has dropped a lot. We found that the original model is very contrast, and but with drag, the model will maybe have a little over reliance because their precision has decreased a lot. And we can find the right part with the number of retrieved contacts increase. The model will the accuracy is much better. So we can see that if we using a greater number of retrieved contacts, maybe it will lead to more reliable generation. So that is our motivation of our recent work rule, which is published in MLP 2024. Firstly, we can see the left part. Too few or too many retrieved contacts as references may not provide effective guidance for the medical vision language model generation. It's very reasonable. If you input too many text report, maybe it will disturb your model to generate some reasonable response. And if you input too few, maybe the model do not get your what you mean. A lot of details in another text report. So we need to calibrate the number of the retrieved contacts. It will effectively control the risk of the factuality accuracy. We can see from the above figure, it's very sensitive to about the number of retrieved contacts. So for second part, we can see from the left right part, the figure shows that maybe the model will over rely on the retrieved contacts. You can see from the first figure, without RAG, maybe the model right, but you know that you cannot guarantee 100% accuracy in your retrieve part. So maybe with drag, the model response is incorrect. So you need to make your model much stronger. You can judge if your retrieved context is incorrect. I can use my own knowledge to answer this question, rather than just generate some hallucination. Yeah. So a stronger fine-tuning model it can effectively balance its own knowledge and the external knowledge, which is the retrieved context. So firstly, how to select the optimal number of retrieved contacts. Actually, here we just use the factually risk control. It's a very simple statistical calibration method to determine the optimal number to ensure the factually accuracy. We just use some high-sense tests on the validation datasets and use the number key, the same number key to on our test set. It's very simple and it's very effective in its synonym. But we do not considering about like the similarity score and a lot of methods we will discuss after that. And for the second part, it's much important. We can see or how to address the overall issue of medical vision language models. Actually, it's a very misalignment issue in the vision language models. We just use first fine-tuning based on the RAG issues. We fine-tune the model by constructing a dataset with preferred and dispreferred response. So the preferred is that correctly the answers which is correct but without the retrieval. But if with RAG the model's response is incorrect, so that we just control like this previous dataset, and it will have a lot of override issue in the dispreferred response, so that we can use principal optimization. It will align the model external knowledge with the retrieved information, so it will minimize the override issue. And for the experiment part, we just use two types of tasks. First is the medical VQA, which is like asking some questions based on your medical image. And the second is medical report generation. It's more like image captioning task in the general domain. Just generate some medical report based on your input image. And it involves, actually the typo, it's involving two modalities. First is radiology, like X-ray. Secondly is ophthalmology, like the fundal images. So it involves 3 datasets, X-ray, mimic cigar, and the Harvard Fair VLM. And the base model we use Lava Med 1.5. And then the comprehension method based on the SOTA decoding based methods. So we can see from the two tables, actually our model is much better than the overall comprehensive methods. So we can see the rule improve factuality accuracy by over 40% on average compared with the previous SOTA methods. The model showed consistent accuracy gains from across datasets, particularly in radiology, such as the X-ray and ophthalmology. It will just significantly improve the factuality. And based on that, we do some another analysis based on our experiment. The individual contribution of RAG, we can see from the application studies, the factuality risk control FRC and KBPT analysis. RAG alone show limited improvement, particularly in some complex cases, which is reasonable. Maybe in the MIMIC-CXR, it's very the text report is very long, so it's very hard to just use a simple retrieval can get a better performance. So which is reasonable, but with some more powerful technique like the FRC and the KBPT, our model will improve a lot. Let me say something. And we analysis the preference data type in the KBPT, which is the preference fine-tuning stage. Actually, our task involving VQA and captioning. So we do know which type of data is will perform better. So we just use and try maybe the caption is better, VQA is better, or the merge is better. So through our experiment, we see that the VQA format is much better. Maybe because they have some details in the analysis part. And the second part is about the comprehension with other medical vision language models. We compare with several other models like Medical Flamingo and radiology foundation models from the Shanghai Jiao Tong University. Our model much better than that, and we do some competitive analysis. Like we use another backbone, which is the LoveMed 1.0. Our model, our methods improve a lot based on that. And we do some case studies in the scenario where the reg mislead the model, the rule restores accurate response by balance the retrieval and the internal knowledge. Enhanced context understanding allow the model to generate the most accurate and reliable answers. So we do some more analysis about how does our method improve the performance. Rule introduce the override retrieve by over 40%. Enhance the model's robustness. Attention analysis reveals that the model shifted the focus away from the retrieval context towards to the internal knowledge, aligning the outputs with factually data. We can see from the this example, maybe they have some incorrect information in your reference, but the original model cannot judge that. So our fine-tuned model can judge that and generate some more accurate response. So RAG is effective and to improve the factuality on both tasks. And we use like the collaborative selection of virtual context number and alignment of RAG are very important. So we do what is next? The comprehensive alignment objective in the alignment RAG. We just analysis about the overlines the one issue in our recent work, but we would like to dive into more, and we can design a general RAG system. Maybe it can input a lot of different domains, different modalities to our system, and we can use the sophisticated retrieval for that. And lastly, maybe we can design a more reliable collaboration selection algorithm considering a relevance score. So here is our latest work, which is called Med-LVLMs, and we firstly we design a domain-aware retrieval maxim. This model can handle different domains of medical images more effectively. Such as radiology, pathology, and ophthalmology. We design a model identification model to adaptively select a corresponding retrieval model given on the input medical image, so that we do not need to train a model specific for one data set. Now we just need to train a model specific for one modality. Secondly, we can see from the our above about FRC, we do not considering like a similarity score, and we do not considering some complex scenario. So in our here, we just do some analysis about the distribution of the similarity score. It varies depending on the complexity of the image and its alignment with the textual information from the data source. So we can see these fixed K methods do not guarantee optimal performance on the target data, as they overlook the similarity score generated during the retrieval process. So to address this, we propose adaptive methods that dynamically select K based on the similarity score of the retrieval context. So the score between the retrieval context over we can see some sharp decline after a certain number of results, maybe near the top 9 in this case. This suggests that the lower information can still include among the top K retrieval contexts when using a fixed case strategy, especially in cases where the fixed value of K is too large. These low quality retrievals introduce noise and some invariant information, which can significantly impair the model's ability to generate factually response. And we design a more complex RAG-based alignment model. We found that we conclude this as 3 misalignment issues. And we formulate this problem in like doing a process of doing homework. Yeah, very interesting. So firstly, it's more like the model will directly copy homework from others. So we need to make the model think it by itself. We can see from the left part. We found an interesting familiar. If you input some unrelated image, it's some with a highly noise, the model can also generate like yes or no. Yeah, it's very weird. It has a lot a third cross modality misalignment issue in the vision models. So in this scenario, we will help the model to avoid blindly copy external information by encouraging the model to rely on its own visual reasoning when solving complex problems. And secondly, we can see this part. The model cannot solve problem by themselves, so we need to help them how to copy the answer in the reference. When the medical vision models are unsure, so our method will teach the model to intelligently use the retrieval context, pulling in the right information at the right time, boosting the accuracy and reducing errors. And the second part is similarly from the rule part. Copy homework is wrong, so we need to avoid inference from the incorrect homework. So our method will prevent the model from being misled by incorrect retrievals, reducing the risk of generating incorrect medical diagrams. So for this method, our improved version, we add two datasets and one modalities. We add the pathology modality and the two corresponding datasets. And we add some comprehension with some recent multimodal RAG methods. So we can see from these tables, we compare more with some like medical doctors and FactMM RAG from the CMU. We can see that our methods significantly improve the factuality than others, and in a lot of modalities, which is it is rare, like the pathology, most of the models perform worse than others. So our models can still perform better than them. Yeah, both on the like close-ended questions and open-ended question, and about the open set generation, like the report generation. And lastly, we also do some like visualization on how does the method improve the performance. Firstly, we calculate the population of errors caused by RAG and compare it to the population after incorporating our method. So the model may directly copy the reference information. We call it copy reference rate. We can see there here, CR rate. Yeah. After applying our method, this rate will drop into 28%. Additionally, the population of errors affected by RAG inference will refer to like over rate, overrides ratio, which is initially more than 40%, and after our methods, it decreased to 8%. Yeah, and furthermore, we can see this figure. The original medical vision models tends to rely more heavily on the text because it's often ignore visual information. So when the retrieval information are introduced, the original model focuses more on the retrieval answers, even if the context is incorrect. So after our methods, the model significantly increases attention to the visual information, and it will reduce the interference of the RAG. Thus, better aligns the model's internal knowledge with these facts. So finally, we can see from the above two RAG-based work, we do a lot of methods and experiment based on that. So RAG is very effective to improve the factuality for medical vision models in the two tasks like VQA and report generation. So both calculated selection of retrieval context number and the alignment based on that are very important. So We just see the next. We just use some like the example about the post-training method on the macro vision language. We do not need a lot of large-scale data set to do this fine-tuning. Just use some like burst fine-tuning on some smaller data set. It can still get a lot of a better performance. So it is our latest work. It's a very small work. We call it like the aligning medical vision models with clinical medical multimodal preference optimization. So firstly, we can see the left part. The overview of our work. It considering of the multimodal data correlation and the clinical relevance score and about the clinical preference fine-tuning. And for the data correlation, we can see this part. The hallucinated text response are generated by the GPT-4o with the reference of ground truth, so that the model can generate some incorrect response as a dispreferred response. And for the visual part, we use some tools to add some noise to the key region of the medical images, like about some key region like about this issue, so that the localized noise will use as the dispreferred inputs. It will encourage the model to focus more on the visual information, the very valuable visual information about this set. So the second, we just use some tools on some medical large language models to quantify the clinical relevance score. It will use like this one. We use the stage of multi-agent collaboration based on the medical large language models to generate some score to judge the dispreferred does it have some medical significance or do not have some relevance, clinical relevance. So it will give a relevance score like the 6 point. And for the visual part, we will just use the tool's confidence score as our score. Yeah, in the visual part for the clinical relevance score, we just use the two score as a weight to the person fine-tuning on the DPO. And so that the model, it will encourage the model to do this clinical person optimization to learn better than how does your person fine-tuning and does it have a significant medical significance. If it is the weight is bigger, so that it will focus more. And we can see from this very simple results we use on the four public data sets is very widely used, and on among them two are VQA format and two are report generation. Our model are very better than all the DPO-based methods, including self-rewarding and the original DPO, and like the recent ST Lava Med from the Salesforce. Yeah. So much better than the original person fine-tuning methods. So anyway, it is very effective to solve this misalignment issue caused by RAG or the post-training methods like the Prof fine-tuning. So what is next for the RAG? Maybe we can focus more on the data used for retrieval and the performance of the retrieval. And for the model fine-tuning, especially for the post-training methods, we can improve the model's understanding and the generalization capabilities from both the text and the visual modalities. Yeah, that's all. Thanks.
Okay, thank you so much, Peng. That was really a amazing presentation. So I did have one quick question to kick things off. So I'm curious, in terms of at least the data set, did you have both contrast and non-contrast scans in that data set to see, what the results or the differences were, at least in terms of the scoring, because oftentimes, at least in a medical context, context, physicians like to get contrast imaging. So I'm curious that you have both contrast and non-contrast imaging in the data sets.
Yeah. Wait a moment. I will. Yeah. For this part, maybe firstly we need to split the dataset into three parts. Firstly, for the retrieval fine tuning. Our retrieval need to training and on the sophisticated dataset in our first work. And in our second work, we just need to fine tuning all the retrieval based on the modalities. So secondly, you need to split one dataset into the validation of the retrieval. And lastly, you just need the dataset to the precise fine tuning. Yeah. So you need to construct the dataset based on your needs.
Okay. And I know a few questions are coming in, but I'm curious. I know you guys focused on using LABA Med 1.5. So what was the decision process in terms of using LABA, say, for example, versus closed source Med-Palm?
Actually, the lava mat is based on the lava checkpoint. Yeah.
Okay.
So their team maybe just use you can see the first maybe slide. Yeah, this part is about the training stage of the lava mat. Yeah, it just uses a lot of the collected dataset and some public dataset to do this fine-tuning methods based on the lava checkpoint.
Okay, all right.
So I have a question for Peng. Um, did, did you guys try to study the effect of the interleaving process on your results? Because from what I can see here on the slide, the different modalities were interleaved. Does that make sense?
Yeah. You're right. I think it's reasonable. Maybe you just need generate some response based on your input data. You need to see what his modality is. If your input is X-ray, you just need to put your image to the radiology retrieval. You don't need to retrieve some text report based on your the whole data source. It is very costly and do not have any improvement. Yeah.
Okay. So just to be sure that I get you clear, you found that trying to interleave data in different approaches didn't really improve results.
Yeah, actually for this part, I think the time cost is very low. We just use the biomedical clip to do this retrieval part. So maybe for each sample, you just need like the a little time. Yeah, I think this is we can accept that.
Okay. Thank you.
Welcome.
Ahmad has a question. Nice.
So I wanted to ask, first of all, great work. So what do you think is the next improvement in the wave of medical vision language models? So do you think that the major improvement next can be done via improving on RAG techniques, or do we need some sort of more intelligent reasoning like chain of thought or something like that in combined with RAG to make it even better?
Okay, that's a great question. Actually, we just do the methods from the RAG to the post training, such as purpose fine tuning. And for our future work, maybe we can focus some like the broad application like ECG, or you can try some like do some diffusion model. You can generate some data based on your a lot of scale to improve the data scale. Yeah, maybe you can focus more about the data.
So, hey, Peng, one of your earlier slides was talking about one of the upcoming papers that you guys are presenting, I believe, in 2025. And I noticed you were talking a little bit about agents. So is that part of the plan to be able to handle with the agents composite clinical scenarios where, you're maybe going from maybe you're going from cardiology back to radiology to another discipline. So yeah, where you have the multi-agent collaboration. Would that aspect of scoring, et cetera, handle composite clinical scenarios?
Oh, that's great questions.
Yeah.
Yeah. Actually, I noticed there have some recent publications about the agent part in the healthcare application.
Mhm.
Yeah, they will use like a role playing system. Use one model as radiology doctors, and another like the ophthalmology, and one models for each department, so that they can collaborate and do this final decision. Yeah, it's very interesting. But actually, so far I did not get that our model can have this performance.
Oh, okay.
Yeah. I think the in this stage, our performance of medical vision language models are still poor. Yeah, we can discuss it later, and maybe you can just use some fine-tuning methods based on your multi-agent collaboration. Yeah.
Oh, okay. And that'd be a good way to handle composite clinical scenarios. Okay, gotcha. Okay. Hey, I know we normally have a question or two from Mayank. So Mayank, we didn't want to leave you out.
We also have Shamim. Shamim
Oh, yes,
also has a question.
Shamin as well.
Thank you for this presentation and the opportunity to ask questions. Actually, I'm curious, but maybe you mentioned and I missed it. In one of the earlier slides, when you referred to clip approach and its application, the paper, did you just use the contrastive learning idea from the clip, or you use the clip's pre-trained encoders? Or, I mean, you fine-tuning these encoders, or you train it from the scratch and use the just contrastive part of idea?
Okay. Thanks for the questions. Actually, it's very detailed problem. In our methods, we just use a biomedical clip and do some fine tuning. We do not train it from scratch. It's very costly, and we do not have such large scale data sets. Yeah.
Okay, thanks a lot.
Plus, do you guys also work on the long context part of it, the long context RAG?
Yeah, I understand the problem. It's a very key aspect for the RAG. Let me find the. Yeah, you can see from our application studies. You can see from the Mimic CXR. Actually, this retrieval context is very long because the text reporting in the Mimic is very long, compared with X-ray. So with the simpler retrieval, you can see the performance actually dropped a lot. Yeah. So the long context RAG is still a problem. I think it is worthy you do some further diving into this domain.
Okay. And plus, do you also consider that the state space models or the hybrid models like the Mamba and the Samba are a viable alternative to pure transformer models? And how does that look in the context of this RAG?
Oh, that's a very interesting question. Actually, I'm not very familiar with Mamba, like this time series model. Yeah, but I think maybe it is worth it trying that, doing like the Mamba-based large language models to this long context understanding problem. Yeah.
Cool. Thanks.
Thank you.
Yeah. So just to confirm, Peng, when you talk about retrieval here, you just do simple retrieval, nothing complex, just simple retrieval, and then it's like how many contexts do you select? Just with simple retrieval.
Yeah. You can see our inference phrase. you just use your input image and into our clip model, and it just retrieves some more similar reports based on your data source. Yeah, just a simple retrieval.
Okay, so you just retrieve just one final report. That's all.
Not one. It's just an example.
Okay, that was what I was asking. If you made, because I know you were talking about factual risk minimization, where you try to select the optimal number of K.
Yeah,
right?
Yeah, that's true.
But yes, but it seems to me that this particular work came first. It was the precursor to that paper. Right?
Yeah.
Or is my assumption wrong?
Yeah, that's right.
Yeah. So the question I was asking is, in that scenario, did you just make use of a random number of selected contexts, or you just had a fixed number of contexts?
So in our MLP work rule, we do not select an optimal model based on one sample. It's just you use a fixed number for all the datasets. Yeah. So
Okay.
in another work here, we select the one optimal context number for each sample, and we contain we considering the similarity score. Yeah.
Okay.
Yeah.
Thank you.
You're welcome.
Okay. We don't have any additional questions in the chat. So I just wanted to put out one more call in that respect to see if there were any additional questions from the attendees. Okay, well, I think we've had all our questions asked, Peng. So thank you again so much for your time.
Wait a minute.
Yes.
Wait a minute. I mean, I would like to get access to the slides, Peng.
Great.
Would that be possible?
Okay. Yeah.
Yeah, because I still think that there's still a lot that I can pick out from that slide. My mind is not necessarily in the space right now to extract what I need. I still think there's quite a bit I can pick out from there, but yeah. So I would like to have access to the slide.
Yeah, I will show you.
Yeah.
Okay.
Thank you very much. It was nice having you. Thank you.
Yes, it was wonderful having you. Thank you so much for attending, and thanks for everyone who attended as well today. And everyone have a good rest of your day or evening wherever you're located.
Thank you, guys.
Okay.
Have a nice day.
Bye.
Bye.